Hey everyone, so this video is on the process of gel electrophoresis. It's another one of our biotechnologies we're going to learn about this year. So the learning intention for this video is to understand how gel electrophoresis actually works and what it is. And we're then at the end of the video going to look at interpreting a gel after the process of gel electrophoresis and see how it actually works. So gel electrophoresis is a process that scientists use in which molecules are separated depending on their size or on their charge. So we often use it in things such as DNA profiling, forensics, things like paternity testing, basically anything with DNA in some way we could use gel electrophoresis, things like genetic research and much more. What you'll see throughout this video is a picture like the one shown on the left. This is an example of what gel electrophoresis results in. And we're going to break down this video, what that actually means and how we would interpret this picture. So scientists have used electrophoresis to separate DNA and compare the different samples of DNA, let's say from a crime scene or from someone trying to get paternity tested to work out who their parents might be. So first of all, we take DNA and we cut it into fragments using restriction enzymes, and we then compare them through gel electrophoresis. So the actual structure of the gel is really important. So electrophoresis gels are made of agarose, which is actually from seaweed, and it's a type of carbohydrate, and it does really look like jelly. Now this jelly is not 100% solid, so it allows some molecules to pass through it, through the tiny, gap. Sometimes it's called a matrix between the bits of gel. Now, the way it works with gel electrophoresis in terms of DNA is that we'll amplify some DNA using PCR and we'll place it into one end of the gel in these specialized wells. And then once they've been loaded, we then will turn this gel on. In other words, we're going to put current that moves through it, and it will actually start to move the DNA throughout the gel. It's a little hard to visualize, but basically you can think about it. This is the gel here, and you can see this bluey liquid is actually DNA. So we're placing it into these specialized wells, and then we turn the gel on, and you can see that this DNA will actually migrate throughout the gel and start to separate based on its size or based on its charge. The other things we add to our gel electrophoresis is a dye. Now this dye means that DNA becomes visible under UV light. So often when a gel electrophoresis is finished, they take the gel and they'll put it on a specialized platform that has a UV light underneath it, and then it shines through and you can start to view the DNA through the gel. They'll also include a buffer solution. It's just a liquid that allows charge to run through it, and this just helps the current run throughout the gel. So when we actually run a gel and we interpret it, DNA has a negative charge. So we put it in the negative end. And then when we turn it on, it starts to move towards the positive end. As obviously we know, negatives will start to move towards the positive. The smallest fragments, so the smallest pieces of DNA, will travel easier throughout the gel, whereas the larger fragments get caught up in some of the gel and take a bit longer to move throughout. So let's say if we run a gel for 45 minutes, you can see that the smallest fragments will be the ones that are closest to the positive electrode, and the largest fragments will be closest to the negative electrode. So that basis means that we can start to compare different gels or different samples in the one stretch of gel electrophoresis. Now we also put sometimes what's called a DNA ladder. Now this is a set of DNA fragments where we know the lengths of them already. So if we know that this DNA ladder has got a 3000 base pair fragment in it, a 2000 and a 1000, we know to expect those on our ladder. And it's act as a comparison tool to compare our results against. So I know it's a lot to take in. We're going to have a look at an example. So let's say that we've got 3 suspects in a crime scene, these 3 characters here. We'll call them Bob, Sue, and John. So Bob, Sue, and John have sections of DNA that are different amongst themselves, and often scientists use sections known as short tandem repeats. So you can see here that scientists are looking at the AGAT repeat, and we can see that Bob has got 7 and 6, Sue's got 4 and 19, and John has got 12 and 14. So you can see it's quite different in the number of repeats. Now, scientists wouldn't know this until they've run the gel electrophoresis. So these fragments are cut out using restriction enzymes. Let's go back, sorry. They're cut out using restriction enzymes. And we're going to start with Bob's first. So Bob's DNA is loaded into the well. You can see this is the negative end. It's going to start moving towards the positive end. So Bob's going to be run, and we could see that he's got 2 bands, one that's at about 7 and one that's at about 6. So that would be, okay, the results for Bob's. Then they do the same process. They'd cut out these repeats with restriction enzymes. They'd amplify them using PCR. Then they'd place Sue's down in the wells down on one end. Again, they'd run it through the gel at the same time. And you can see that she's got a really, really small fragment, 4 repeats, and it's moved really fast throughout our gel, whereas the massive fragment, the 19 repeats, hasn't moved very far from the original. So we can see that would be our interpretation for Sue. And then same again for John. We load his gels, we'd run it through electrophoresis, and again, you can see that he's got 2 fragments at around 12 and 14. So scientists then might use this results and compare it against a sample they found at the crime scene, and they're trying to see which one matches up. So if the crime scene, for example, matched against Bob's, the first lane, you would start to imply that maybe he was the suspect at the crime scene. And they then use that process, and they do this many times at many different sites or STR sites. And eventually, if there was so many matching up, the odds would say that that's definitely the person they were looking for. So in review, it's a gel electrophoresis is used to compare DNA fragment lengths, and it relies on PCR and restriction enzymes to work. And is often involved in DNA profiling or genetic testing as well. So the key aspect you need to know is that the smaller fragments will move faster than the bigger fragments, and they move from the negative towards the positive electrode. And then we can start to interpret the gel after it's run through its course. Hope this video helped. Thanks.